A lot of physics students find Lagrangian analysis confusing when they first see it. I did, and in thinking of ways to explain it to myself and others, here's what I came up with. We're in 3D space right now, so in Cartesian coordinates, you can move sideways right and sideways left, the y-axis, back and forth, the x-axis, and up and down, the z-axis. 3 dimensions. A particle in empty space has 3 degrees of freedom, but for you, a particle constrained to the surface of the Earth, your vertical position is fixed by the constraint z equals 0. And this is the Earth, and this is you on the Earth. The first step of using the Lagrangian to find equations of motion for a system is choosing generalized coordinates. The trick is to choose coordinates that automatically satisfy the constraints. For example, if a particle is constrained to move on a sphere, spherical coordinates make one coordinate constant, r, and the constraint disappears from the math. Because if you think about it, r is constant all along the sphere. Remember, you may not understand everything about a problem at first, but as you work through more problems, you will understand more and more. So it's okay if you don't understand everything I'm saying right now. That's just physics. Okay, so we have a thin, straight wire at a fixed angle alpha with the vertical. It rotates around the vertical at a constant rate omega. A bead of mass m is free to slide without friction on the wire. The only forces present are the constraint force and gravity. Find an equation or equations of motion for the system. In this example, I chose spherical coordinates instead of cylindrical. Try to see if you can figure out why. So our generalized coordinate is r because that's the one that can change. And our constraints are theta and phi because we're given theta equals the constant alpha and the angular velocity phi dot equals the constant omega. So we know that the derivative of theta is 0 because alpha is a constant, and we know that the antiderivative of omega is omega t. These constraints help us simplify the Lagrangian. The Lagrangian is just L equals T minus U, kinetic energy minus potential energy. And if we're working with vectors as we are, you take the dot product of V with itself instead of V squared. So we're using spherical coordinates and we use spherical velocity. Since we're given theta dot equals 0, we can cancel out a term here and we can plug the constants into the formula. So here is our kinetic energy term. And our potential energy is just mgh or mgz, and if we go back to the diagram, so SOHCAHTOA, cosine of alpha equals z over r, so z equals r cosine alpha. So that's our Lagrangian, L equals T minus U, and just put it all together. Now, here's the Euler-Lagrange equation. This thing right here. It looks scary at first, but you just do it in chunks. So chunk 1, partial L over partial R. Go back up to the Lagrangian, underline all your terms that contain R, and take their partial derivative. See my review of partial derivatives if you need help. Chunk 2, partial L over partial R dot. Oh wait, let's finish chunk 1 first. Okay. Chunk 1. And chunk 2, partial L over partial R dot. So you go back up, circle your terms with R dot, and take the partial derivative. And then, all right, okay. So now we have the time derivative of that last one, partial L over partial R dot. So note that you don't need the chain and or product rule when taking the partial derivatives, but you may need the chain and or product rules when taking the full time derivative. So now we have all the chunks. So we just put them together just like they're in the Euler-Lagrange equation. And you will have as many equations of motion as you have generalized coordinates. So here is after we put it together, cancel out the m's, that's our equation of motion. What's the point of all this? It's easier than making a free body diagram to come up with equations of motion for more complicated systems. And there it is. Yep, there it is, our equation of motion.